Hello, I am David Norris, who is the owner of this site and planning to set up a photovoltaic electronics business in Western Africa. I thought it would be very useful to have a quick demonstration of just how you do the key thing: convert solar energy into solar power, or as the technical name is, photovoltaic power. So this is just basically a working and introductory design. I've made the circuit diagram available in this video without the specifics too much, and certainly not the firmware, because this design actually forms the basis of a commercial design. But let's have a look at how you convert solar power into alternating current, which will power your mains appliances, as everyone wants to do. Now, the first thing I'm going to do is introduce this software. It is called Proteus, and it is one of the most advanced circuit design and simulation packages in the world. So, I'm just going to explain the basics of how it all works. And I'm going to zoom in on specific areas of the circuit diagram so we can look at what is actually going on. Now, when we look at this, we can see that the solar panels, these are virtual solar panels because of course this is a simulation, but of course they output direct current, DC, as you can see, evidenced by the black negative and red positive wires, whereas alternating current changes its polarity 50 times a second. In most of the world, Europe, Africa, Asia, Australasia, it is 50 cycles a second, whereas it is 60 cycles a second in North America and South America. So, since we're interested in the African market, we are set to 50 cycles a second, and to change it would involve changing the firmware. Now, what we can do is zoom in on first the basics of how this is all done. The microcontroller is used to generate a clock signal, and as this is a three-phase design, it is the basis, the building block of a more sophisticated design capable of serving multiple customers. We are going to use three-phase. Individual dwellings and small commercial premises would only be connected to one phase. So I need to generate a clock signal for each of the three phases with a high degree of accuracy at 50 cycles per second, 50 Hertz. To change to 60 cycles would involve a firmware change, but I'm not going to reveal the firmware for the microcontroller, which is a popular PIC 16F877A microcontroller. Many of my designs use microcontrollers for control monitoring purposes, and of course actuation in the designs which I have, which keep solar panels accurately aimed at the sun. So that is what's going on here. We've got a clock signal for each of the three phases, and these are 120 degrees, or a third of a cycle out of phase, as is the case in a standard three-phase system. Now, the main supply is a nice clean sine wave. Have a look what a sine wave is, you'll see in a moment. And of course the microcontroller as a digital device outputs a square wave, where 0 volts is binary 0 and plus 5 volts DC is binary 1, but we don't need to worry about it. We just need to convert our clock signal into a sine wave I will not detail too much why, but there would be serious problems if I were to feed mains appliances a square wave, especially those which are inductive in nature, such as transformers or motors, and indeed, you'll see in a moment we have a transformer in this design. We need a sine wave. So, this filtering area is there to convert the square wave from the microcontroller into a sine wave. So I use two stages of filtering, and because each filter also reduces the voltage, it is a voltage divider as well as a low pass filter. I have to regenerate it using an operational amplifier. So at this point, the signal, the sine wave is tiny, but you will see it displayed on a virtual oscilloscope as well as the original square wave from the microcontroller when I start the simulation. Now, in reality, I would have a whole bank of these in order to increase the power yield, which is otherwise limited only by the output of your solar panels, and I've done the calculations to determine how much yield, as it is known, I will get per square metre under African conditions. Suffice to say that African conditions are much better suited to generation of photovoltaic power than a European winter. So here we boost the power, and now we have rather more, about around 30 volts alternating current and 1 amp, pardon me, and I've got a little bit of a cold at the moment, and you will see that, of course, we need higher voltage in order to run mains appliances. So, for each phase, as well as the filter circuit, you will also see a step-up transformer where we convert high current and low voltage to higher voltage and lower current. This demonstration design with one power transistor will output enough power to have 1 amp per phase at 230 volts root mean square. Root mean square is basically the average voltage, because with alternating current the voltage is continually changing, and for example a bulb will light with the same brightness, it delivers the same power as a constant 230 volts direct current would be, but you cannot use transformers on DC. Finally, as this is a three-phase design, I am using a three-phase transformer, and you'll see that the phase to neutral voltage is 230 volts RMS, but as in any other three-phase system, the phase-to-phase voltage is 400 volts, because 230 times the square root of 3, which is a little more than 1.7, is 400 volts. So we say that this is phase to phase 400 volts and phase to neutral 230 volts. And that is the reason why we have this warning here. It would be possible to receive a 400 volt shock if two phases were touched simultaneously, and even 230 is more than enough to kill. So I will not be releasing the basics of this design, how the firmware works, or go into it in too much detail. This is a demonstration video. If there is enough power to run mains appliances, it is enough power to kill, and I do not want novices to try building this themselves and electrocuting themselves. So the only thing that remains, now I've explained this, is we need to see it in action, do we not? As we British say, the proof of a pudding is in the eating, so let's do the simulation and watch what happens. It'll take a moment, but straight away you can see that the microcontroller is outputting our square wave at exactly 50 cycles per second, with a time period of 20 milliseconds. The time base is set to 10 milliseconds, and it takes 2 divisions, 20 milliseconds to complete a cycle, which is exactly what you would expect. And after the filter, the second oscilloscope is connected to the output of the filter, and you can see that before amplification, here is the sine wave output. It is not quite perfect, however, it is a better sine wave than is output by many commercial inverters, which are modified sine waves, so it is plenty good enough. And as you can see, again, each phase is a third of a cycle apart, as you would expect, 120 degrees. So, for example, you'll see that this, if you compare with yellow phase, blue phase is actually a third of a cycle ahead of yellow phase, and red phase is a third of a cycle behind. And then finally, if we zoom in, we will see that here goes, you've got a nice output of 230 volts within tolerance, and you'll see that you've got that on each phase, and that, as I have just explained, is how you convert solar photovoltaic direct current into three-phase mains alternating current. I hope you found this an interesting demonstration.